joining me once again, or if it's your first time here, thanks for joining me. I hope that your journey through this educational whirlwind provides you with everything that you were hoping for. The one thing it won't provide you with is the kind of videos I used to make here on YouTube. Can't be doing that anymore, apparently. So we're going to have to change our ways. We just have to be a bit agile. If you want to watch that other kind of stuff, you can do that on other platforms on which I also have channels. In the meantime, we're doing science. And what we're going to do is we're going to do it properly from the ground up. And the way I'm going to do that is I'm going to kick out every block, every foundation block of everything that builds your view of reality probably. Most likely, I'm going to kick out everything that you think exists, everything that you think is real, everything that you think is objectively true, and show you how that it is actually, in fact, otherwise. Why am I doing that? One, because I want you to start thinking critically as a scientist. I want you to start challenging people who say things like, science shows, or we have good, strong evidence that, or any of those kind of things, because as it turns out in reality, it's not so, actually. Especially people who are very, very sure about themselves when they talk about what the science shows us with regard to human nutrition. So that's why I'm doing it. I'm kicking all the blocks out. If that upsets you, I'm sorry about that. It's the way it is. Stick around, though, because there's a lot more coming after this when we start putting better blocks back in place upon which you can build the foundation of a much more rigorous fort or castle of knowledge about human nutrition science. Science in general as well, and probably make you a better, well-rounded human being altogether. So, big claims, I know. However, I don't guarantee any of those things. I'll do my best to provide them for you. What I can tell you, however, right up front, is that the biggest cause of not achieving happiness in your life is failure to hit the like button and subscribe to my channel. So, if you take care of those couple of things, that will probably be a good start. Right, so this is the first in my new lecture series, my new course, if you like. This is called Human Nutrition Science 101. And the working concept really around this first lecture is, really it's about how is it that we think we know so much when really we know so very little. This is a lecture about the very nature of reality itself, actually. The very most fundamental building blocks of the universe and what we know about those, etc. That's a very long title, so I thought I'd boil it down and just call it, Do You Exist? ? AKA, what is matter? All right, so let's get started on that. But before we do, let's hear a little promotional bit of doings from our good friend, the Professor. Professor. Here is a lesson I used to give to my postgrad research students on their first morning. We have an overall figure made from two right triangles. These are sized 5 times 2 and 7 times 3, and also two other identical but opposed irregular blocks as shown. The overall figure is sized 12 times 5 and has a fixed area, which we could calculate. If I rearrange these puzzle parts into another configuration, their area remains fixed. Oh, it seems I have now proven myself a witch, for I have undone reality itself. Seriously though, explain this, if you please. Okay, excellent work, as usual, Professor, of course. Right, so, reality, do you exist? What's all this about anyway? Okay, well, our understanding has developed over, most notably, the last 115, 120, perhaps slightly longer years, where we have now come to a point where we have a pretty good working theory of the nature of reality, the constituents of the universe, what makes up every little thing in the universe, what makes up you, and why, well, not why you are here, but what is it that you are or are not actually in so being here, or perhaps not being here as the case may be. So let's go right back to the very beginning. Let's kick out all the blocks, just clear your mind and clear the slate of everything. Sit up straight, pay attention, stop throwing paper darts, and just clear your mind of everything and make it a blank space entirely. And imagine at the beginning of some people's favorite book where it says, in the beginning there was nothing, and then God said, let there be light, or something like that. The story here is not that far removed, really, and it does require some leaps of faith, really, for people who think that their experience of the world has provided them with some surety about some facts. Like, if I said to you, dear viewer, do you even exist? Are you an actual thing? Are you composed of stuff, matter? You would say, well, of course I am. Why would you even ask that? That would seem ridiculous. Well, let me explain to you why you should question it. Number one, it's because you should question everything. Questioning things is exactly how we do science. Questioning science is even more scientific. In particular, the way you do science is you question established science, and you do everything that you possibly can to attempt to falsify it. That's the whole point. That's what we're paid to do as scientists. However, in today's society, we are often discouraged, quite forcibly, in fact, from raising our voices and saying anything of any kind of even perceived dissent against established science, when, in fact, that's how you do science. Anyway, that's for another day. Right. What are you made out of? What is this stuff that makes up you? Well, you are made up, literally, actually, as it turns out, you are made up of atoms of matter, atoms of stuff. Okay. An atom is the smallest unit of elemental substances in the universe as we understand it. Hydrogen, helium, etc. Onwards down the periodic table. An atom is a single piece of fundamental stuff. So we thought anyway, for quite a long time, until quantum theory came along and showed us otherwise. But let's think about an atom just for a moment. How big is an atom of stuff? Okay, well, the diameter of one atom, irrespective actually of which particular element that atom is, they're all about the same size, actually. They're all about the same diameter overall, and the overall diameter of an atom is a measurement of a length, or like a diameter, which we refer to as an angstrom. An angstrom is 10 to the power minus 10 meters. Okay, so what is that? Well, if you take a meter rule, roughly analogous in size to a yardstick, and you divide that meter rule into 1,000 even sections, millimeters, or thousandths of a yard, if you like, that is 10 to the minus 3 meters. Take one of those millimeters and split it into 1,000 equal segments. That is a length of distance which is 10 to the minus 6 meters. That is what we also call a micron. It's also where we get the name of the piece of equipment that we look at things at that size and smaller, and it's called a microscope. A micron is about the limit of the human vision to detect that there is anything there at all. Not that we could see any detail of something that's a micron at that size, but we can see that it is there. If we've got good eyesight, that is. About the limit of human vision there, 10 to the minus 6 meters. All right. If we took that micron and we divided that micron into 1,000 equal segments, each one of those will be 1 to the minus 9 meters across, or in length, if you like. Okay? An angstrom, being 1 to the minus 10 meters, is 1/10 of one of those. So it's like really, really inconceivably small, beyond our ability to conceive of on an everyday scale of being anything of any kind of utility. We know that atoms do exist. We know that they behave in exactly the way that we would predict that they might behave based on the way that we have modeled the things. Crudely, we've made some attempts at actually viewing one using an electron microscope type thing, where a kind of an image, if you like, of one has been kind of proposed, but nobody's ever actually seen one. However, they're there, they're real, they do exactly what they would be expected to do, very predictably, pretty good model. All right, good. So that's the width of an atom, 1 to the power minus 10 meters across. Now that distance is the distance across the outermost or valence electron shell, sometimes called an electron cloud, which it really isn't a cloud. Sometimes called an electron orbital, and it really isn't one of those because electrons don't orbit. I'm going to use the term shell, valence electron shell. So usually, again, irrespective of what atom it is, generally the outer electron shell tends to be at about the diameter that we've been talking about, around about 1 to the minus 10 meters. Okay. Obviously, more electron shells, you'd think it would the size of the atom would get bigger and bigger, but also the nucleus, where most of the mass is in an atom, gets bigger and bigger as you get more and more electrons. That's why it's got more and more electrons, and as such, it has more pulling power of those electrons and pulls them in closer. So you actually end up with about the same size, 1 to the minus 10 meters. Okay. This nucleus that I'm talking about, the nucleus contains, depending on which element it is, a number of protons, positively charged, electrochemically charged things, and neutrons, electrochemically neutral things. Both protons and neutrons have mass, and that mass is roughly 2,000 times the mass of an electron. So the vast majority of the mass in an atom is in the nucleus and not in the electron cloud or shells or orbitals that surround that nucleus. Okay. The diameter of the nucleus of an atom for the largest of the elements with multiple protons and neutrons, the nucleus diameter is around about 10 to the minus 14 meters. So what is that with respect to our original angstrom? Well, it's 10,000 times smaller than the electron orbital. So you've got an electron orbital with a nucleus in the middle that's 1/10,000th the size, diameter. Okay, that's what you've got. Now that's in the bigger elements with the more protons and neutrons. Single protons and neutrons have a diameter around about 10⁻⁻15 meters, which is 100,000 times smaller than the electron shell orbital cloud. So you have an electron orbital cloud shell, and you have a nucleus which is 1/100,000th the size of that, and almost all the stuff, the mass that's in that atom is in that 100,000th of that space. Okay? So let's go with an analogy to give us some kind of idea of that. If the atom diameter was a mile across, which is 1.6 kilometers for those that speak the new money, then the nucleus size at 1/100,000th, let's say it's an atom of hydrogen, then that proton in the middle of that hydrogen atom would be 1.6 centimeters diameter out of a mile. Okay, which works out to about 0.64 of 1 inch, if you speak the old money. Okay, so that tells us that almost all the stuff, almost all the matter is in a tiny, tiny space right in the middle of this massive, relatively massive area. Okay. Now, next point of interest. Electrons have mass. And we'll talk about mass in a bit, so we'll describe what that is. Don't panic. In the meantime, all you need to know is that electrons, nominally, not to think of it this way, but to give you some kind of analogy, you could weigh an electron. It has a weight in which you can express in kilograms if you want to. It's not expressed that way generally because of the way the math's done. It's expressed as a number of electron volts. The mass of an electron, that's for another day though, don't worry about it. Okay. Anyway, it's a very, 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 very close to zero weight, but nonetheless it has a weight. It has mass. So you might think, well, therefore it is stuff, because stuff has a weight. Except you'd be wrong, because electrons have the exact spatial dimensions, x, y, and z, of none. None at all. They are a point particle. Stuff has to have a physical presence. Electrons do not qualify as having a physical presence because they take up no space in our four-dimensional space-time. None at all. So that electron shell of a mile wide is actually empty space. And the only way it interacts with other atoms of anything is by interactions between electrons, which I'll talk a bit more about at some point should it become appropriate for me to do so. All right. So there's no actual stuff there at all. So all the stuff, therefore, is in the nucleus, that tiny little thing right in the middle, that minuscule little thing right in the middle. Okay. Protons and neutrons are given a spatial extent. They are. I've just given it to you. I've said it's a proton and a neutron are both around about 10⁻⁻15 meters across. In the bigger elements, with more of those clumped together, the whole nucleus is about 1 to the minus 14 across. That's what it is, pretty much. However, what are protons and neutrons made out of? What stuff is there that weighs almost all the weight that's there? Well, as it turns out, protons and neutrons are made of quarks. And quarks are also point particles with no spatial extent. None at all. They in fact take up no actual space. They do exclude, however, electrons to a certain distance because of the strength of their positive electrochemical charge. And they do exclude other nuclei of matter because other nuclei of other matter have positive electrochemical charges. Right. So that's how stuff is said to take up space, but there is no stuff. There is no matter. There is nothing that actually has a spatial dimension. You perceive yourself and others and all other things to have a spatial dimension in the thing that we perceive ourselves to live in, space-time, a four-dimensional fabric made up of quantum fields, apparently. But that's not a reality. That's a perception. Reality requires actual stuff to actually exist, and you don't. Oh dear. Oh dear. All right. So, typically, classically, matter is defined as that which has mass. So, by that definition, a football has mass, a cricket ball has mass, an anvil has mass, a person has mass, people are made of atoms, atoms have mass. All of those things are stuff. They're all physical materials, even though none of them are physical materials, because none of them take up any space at all. Because space itself seems to be a construct, seems to be an illusion in which we think we live. Okay. Right. Mass, in fact, is not a measurement of amount of stuff, because there is no stuff. Mass is actually consequential to another thing called inertia. And in fact, it is also the means by which we interpret what mass is, by looking at the inertia of a body of stuff. Okay, inertia is the resistance to change in momentum. How much force do we have to apply to a thing to get it to change its state of movement in space-time from what it's doing to doing something different from that? And it's that thing that tells us what it weighs, what its mass is, the way we interpret it as having a weight, the thing that our muscles is working against. All things that are made up, all perceptions, none of them reality, because there is, as I said, no stuff. Okay, so fine then, what is inertia? Inertia is, again, a construct because it's about the apparent resistance of apparent stuff, apparent things made of apparent matter to change their apparent movement through an apparent fabric of space and time, none of which can be objectively shown to exist at all. Okay. Inertia can take any value below infinity for a given body of stuff. Why can inertia not be defined as infinity or perceived as infinity? Well, because inertia is the thing that causes us to perceive that something has mass. If something had infinite inertia, infinite resistance to change in momentum, then we would also perceive it to have infinite mass, and anything with infinite mass would draw all other things in the universe to it immediately by the force of gravity, which we also know is a thing that acts between any two bits of mass. And we know that doesn't happen. We've made estimates of the mass of the universe, the weight of the universe, if you like, and it's very, 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 very large indeed, but nowhere near infinity, because it doesn't matter how large a number is. If it's not infinity, it's nowhere near infinity. So there's your proof for the fact that inertia has to be below infinity for any given body of stuff or mass. Good. Okay. Any object or thing which has no capacity to change its observable speed, velocity, is in fact not moving at all. Photons are an example of this. Photons do not move. Photons connect 2 points in one's relative experience of space-time from their inertial frame of reference, and we perceive a photon to have left one place at one time, and at some time later arrive at a different place. And we perceive it to have travelled or moved through space and time at a certain velocity. That velocity is c, the speed of light. It is always the same for every observer in any inertial frame of reference. However, from the frame of reference of the photon itself, it connects those two positions in space-time instantaneously. Because when something is moving at the speed of light, which is actually not moving at all, the spatial distance between any 2 points in the universe is truncated to such a degree as to be zero. There is no distance, ergo it takes no time to move from position to position, because positions do not exist from the point of view of the photon. That's why we're often told when we see the light of a far distant star from thousands and thousands of light years away that we're actually looking at a picture of that star as it existed thousands and thousands of years ago. Today it would look quite different were we there and could look at it now, because those photons took no time whatsoever to connect those 2 points in space-time. It didn't move. It isn't moving. It does not move. It cannot move. It is not stuff. It is not matter. It has no mass. And that's what we measure its mass to be, in fact, zero. All right? So, why am I saying the photon is not moving between the far distant star and here? Well, because movement requires time. Movement is translocation from one place to another place over a given period of time. No time passed for that photon. It did not move. It cannot move. Ergo, its resistance, I guess, to change in momentum is none. Well, it's undefined, or it's infinite, in which case it would have infinite mass, and it doesn't have infinite mass, so that's not right. It must be undefined. Interesting stuff, isn't it? So, anyway, let's get back to this momentum for actual stuff, things that have mass. And let's use a classic Newtonian equation, which is true to all intents and purposes at classical scales and in everyday life. And that is that momentum is equal to a mass, an amount of stuff that we can weigh and measure, even though it's not there, multiplied by the velocity in space-time in our frame of reference that that thing is moving at. Pretty straightforward. Works to all intents and purposes. It's never been proven wrong per se for the context in which it is useful, that is at the large macro scale. However, it breaks down when we get down to very, very small things that have, for example, no spatial extent, or even more confusingly, no mass. Because a thing with no spatial extent, difficult to say where it is, in fact, impossible. You can take that one up with the unsureness concept. We can know a lot about the velocity of a particle, and in so doing we give up any hope of accurately measuring its position, or we can pin down its position very accurately, in which case we give up any opportunity to know much about its velocity. It's one of those weird quantum things. Sorry about that. Anywho, let's take the example of a photon, which we've already spoken about a bit. A photon that has no mass, actually, from our relativistic frame of reference or anybody else's frame of reference in their reference of space-time, their inertial frame. And indeed, the photon itself from its own frame of reference has no mass, because mass is provided for by inertia, and it has none because it's not moving and can't move. So it doesn't have any mass, so the Newtonian equation won't work, because it would be the momentum of a photon would be its mass, which is 0, times its velocity, which is the speed of light, and 0 times the speed of light is 0. Ergo, a photon cannot possibly have any momentum. Except jolly old Einstein wrote a paper in 1905 about the photoelectric effect, where he proved that that was not so, because he was using photons of light to knock electrons out of orbitals and evolve electrical current in so doing. Oh dear. So they do have momentum. Right. So another sum had to be proposed and put together of what the momentum of a photon actually is, for example. And it was determined as being momentum is, in this case, equal to h, which is a constant, Planck's constant as it turns out, divided by lambda, where lambda is the wavelength of the photon. In other words, the momentum of a photon is determined by its wavelength and not by its speed, because its speed is absolutely fixed, both from its own frame of reference, no speed at all, and from everybody else's frame of reference as well. No matter how they are moving and at what speed or where they are in the universe, everybody agrees it's c. Okay, so in other words, it's not moving. All right, good. So that's how that one all pans out. The momentum, if you like, of a photon is best described by its wavelength of the wave function describing it. Okay, good. You can also apply this momentum equation to other point particles that do have mass as well. When those particles are pushed to speeds close to the speed of light, where the classic equations break down and more relativistic ones need to take over. All right, good. Okay. So we've already established that because photons have no mass, they are not things. The reason that they have no mass is because they have no inertia, and the reason they have no inertia is because they do not interact with the Higgs field. It is the Higgs field that gives things inertia. Okay? The Higgs field is the thing that causes a thing to have a relative or relativistic velocity less than exactly c. That's what inertia is. And it's that thing that causes us to perceive that that thing has a mass, a heft, a weight, if you like, a resistance to change in the momentum that it does indeed appear to us to be expressing. Okay? So remember that inertia is the thing that provides for and is the cause of mass. Classically, inertia was thought of as an intrinsic property of mass consequential to mass, and mass was the bottom of the rabbit hole. There was nothing that explained what mass was or why mass was. It was just mass is fundamental, and its fundamental property is it has inertia. It turns out to be actually 180 degrees the other way around. Inertia is the fundamental thing, and it's because of the interaction of various quantum fields with the Higgs field. It's a perception and not a reality, and it's that perception that causes us to perceive the reality of mass when in fact mass is an illusion. Okay? Let's get back to mass for a moment as well. Mass, when we talk about mass in physics, we're talking about rest mass. Okay? Rest mass means the mass of something that is not moving relative to our inertial frame. That's what that means. Given that you cannot bring a photon to rest because it doesn't move anyway, therefore its momentum is undefined and its effective mass is none. And that's why we perceive its mass to be none and measure its mass to be none. And every single experiment that's ever been done has backed us up that its mass is none. Okay, good. It's all falling together, isn't it? Lovely. Now, of course, none of this is actually really proof of anything. It's just a simple, intuitive way to see why it is that photons don't have any mass and other things do. It's a series of equations. It's a series of conceptualizations, constructs, fields, quantum theory, all of that. What you need to know is that every single test of quantum theory that has ever been experimentally undertaken has agreed with the theory. It's at a level of agreement that's far above anything else in science. It is a pretty watertight model. It's something that is intuitively difficult to accept and understand as being anything to do with reality until you understand that your reality is itself an illusion, actually, and as such, the rules of your reality have got nothing to do with the rules of the universe, and the mathematical descriptions of quantum theory are the things that are valid and robust, and your view of reality is not, I'm afraid. Sorry about that. However, if you want to get into and learn more about the robust and mathematical proofs of the lack of the photon rest mass and quantum theory itself and all of that, look at Symmetry Theory, which was put together by Emily Noether way back when, in I think about 1915, I think it was. Specifically with regard to the photon mass, you need to study U1 gauge symmetry from quantum electrodynamics, and that will explain it to you mathematically, or not. Probably not for most of you. I wouldn't bother, but that's where you find it if you want to. All right, good. So mass, ergo resistance to change in momentum, which is what mass is not a fixed thing either. Because remember we said rest mass? Something that's brought to rest in our frame of reference has a mass that we can measure. Okay, if it's moving in our frame of reference, its mass changes. And it takes a certain amount of force or energy to speed things up or slow things down because they have inertia. Isn't that amazing? Okay. In relativistic calculations, for example, that means when we're talking about things moving at a much higher percentage of the speed of light to what we see in our everyday experience, the velocity of point particles like electrons that do have a mass tends to increase. So the more you push an electron, the more energy you put into an electron, the faster you make an electron move in space-time, the more energy is required to get it to that speed, if you like. And that's not a straight line relationship, as you might expect. You might expect that the energy would be down here for one speed and up here for another speed, and there'd be a straight line throughout the range of speeds. Not so. Actually, it's a curve such that, well, I'll give you some numbers so that you can mull them over in your head. If you had an electron at rest and you sped it up to 0.5 times the speed of light, that would cost you an input of energy of 7.83 times 10 to the 4th power electron volts, which is also the way that we measure the weight of an electron, because its kilogram mass is, yeah. All right. Let's say, however, we want to take an electron at rest and we want to accelerate it to 0.9 times the speed of light. That's going to cost us 6.55 times 10 to the 5th power electron volts. Okay, at 0.990 times the speed of light. Now it's 3.08 times 10 to the 6th power. And if we want to accelerate it to 0.9999 times the speed of light, that will cost us 3.53 times 10 to the 7th power electron volts to get it there. So the closer and closer something gets to the speed of light, the more and more and more energy is required to push it that little bit further towards the speed, the speed of light. That's also the reason that objects, things with mass, cannot travel the speed of light, because the energy to get them there is infinite, and nothing has infinite resistance to momentum change, infinite inertia, because if it did, it would have an infinite mass and there'd be nowhere else in the universe because everything would collapse in. There you go. That's why the speed of light is an unattainable speed, and it's the speed limit of the universe as we perceive it to be. And it's actually no speed at all, because a photon moving from place to place does not take any time to do that, because it's not moving. Oh, I hope this is going up your flagpoles. I'm really enjoying myself. Never mind. That's how it is. Okay. So there's a bunch of stuff out there that has mass, but actually is not stuff, because it doesn't have spatial extent. It's not a physical thing. It's point particles, or collections of point particles that interact with different fields and cause different forces. And those forces are attractive or repulsive or neither. And that's the thing that gives things a sense of distance and spatial extent and all that kind of stuff. The main things that we experience in our everyday life, or the things that are important to us in our everyday life, that are stuff because they have mass but are not things because they don't have spatial extent, are protons, neutrons, and electrons. Okay? For an exhaustive list, however, of all the things that are stuff, that are mass, but none of which is stuff, you would have to look at the standard model of particle physics. So go and do some study on that. There's all sorts of other point particles that are not the things that make up protons, neutrons, and electrons as well. But none of those things are stuff. They're all point particles. There is no stuff. Stuff doesn't exist. So therefore, neither do you. All right. So the take-home messages of this lesson were, we started out with the question, how is it that we're so very, very sure about things from science, and what science tells us and what science has established, and what experiments have told us about human nutrition and stuff? Well, I'm dispelling all of that by kicking out the most basic block and saying, well, you can't even prove you exist. So why are you so sure about what you think science says, especially considering those of you who say that kind of thing have no idea what science even is, or what it can and cannot achieve? So the question was, do you exist? The answer is, well, apparently you perceive yourself to exist. I think, therefore I am. I must be a real thing. I must be a real phenomenon. I must have some objective existence, except that's wrong, because objective was the key word there. Object means stuff, matter. There is no matter, there are no things. So in reality, objectively, what can we say about your existence? It isn't, and neither are you. So the only place you exist is in your own mind. Okay, good. And me and mine, and collectively in all our minds, we all think, therefore we all are. But in terms of objectively, in terms of measurement of actual stuff, none of us exist because stuff doesn't. Okay, good. I hope that is as clear as it possibly can be. You are a being of energy. Energy is a construct, and therefore you too, ergo your very existence, is and are in effect constructs. Okay? Is there any objective proof possible that you exist? No, sorry, it can't be done. We just have to go with what we can conceptually theorize on the basis of our mathematical interpretations of the universe and subject those predictions to observation to see if they match. And they do for quantum theory. So therefore, unfortunately, there's the answer to whether you exist or not. And the answer is no. Sorry about that. Well, yes and no. I hope that's clarified things for you. I'm sure that you're very glad you've spent the last 45 minutes with me learning that. The answer is yes and no. That's going to be the answer to many, many questions throughout this course, by the way. I'm just foreshadowing it so that you kind of get the idea that that's what's going to be happening here. Okay. That was the second take-home message, really. So the first take-home message was you apparently exist, but there's no proof that you do. That's point 2. Point 3 is that although none of us exist literally or objectively, we all exist apparently. And in my view of reality, apparently most of us, or some of us at least, agree on a set of rules surrounding scientific assertion making. And we agree that it requires hypothesis testing via observation of phenomena under discipline, control, and that doesn't exist in human nutrition science, I'm afraid. There is a lack of sufficient or acceptable randomization of populations at the outset. Populations that are selected are often not genetically identical, homogeneous research twins. They're invariably not separated at birth or even beforehand and locked into controlled lab situations and kept there their whole lives under observation and control for any confounds and all of that kind of stuff. Often the statistical powering of such studies in human nutrition science is completely substandard. The limitation of all sorts of uncontrolled degrees of freedom that destroy the validity of assertion making is almost impossible to achieve, let alone even attempted in most studies. And most studies that also want to talk about long-term health effects of various aspects of nutrition are not of a long enough duration to be able to inform upon that. So there you go. We started out with, do you even exist? And we ended up with, why is nutrition science as we know it not science at all, but actually an area of ring-fenced ideology, personed largely by individuals with careers to protect, bottom right-hand corners to subserve, funding sources to keep happy, and nothing to do with science at all. There you go. Hope this has been worthwhile. I hope you stick around the channel. It does lighten up a bit. It gets a bit less difficult to understand as we go along. I just needed to kick all your blocks out first so that your minds are open to pretty much anything that I'm going to tell you going forward from here, because you really do need an open mind to get your brain working the right way around this stuff. So thanks for being here. Join me for lecture number 2, which is just called Calories. Guess what that's about? See you then. But before you go, let's hear a bit more from the professor about something. Professor, off you go.
And here is the answer to the Curry's paradox poser. The problem is you probably assumed the overall figure is a right triangle. I led you to assume it. The theta angles of right triangles 5 times 2 and 7 times 3 are close, but not exact. The 5-2 is 21.8 degrees, while the 7-3 is 23.2 degrees. The so-called hypotenuse of the overall figure is actually 2 sides with a vertex, which falls inside where a straight hypotenuse line would actually run in a 12 times 5 triangle. This is not a triangle. Conclusion. Always check yourself for underlying assumption in your logic. The easiest method is check. Don't assume.
you.